I'll keep the intro short because I know you have a lot to cover today. And also you
No, I
can,
think I kept the slides very simple. No math.
interesting. Okay. Okay. Rishabh has been here many, many times now, but we always have new people here who are attending DLCT for the first time. So I'll introduce you as a frequent presenter at DLCT, but also a researcher at GDM that I much respect. Whenever I have any question about RL, and these days about LLM, I'll reach out to you. So
Maybe. Because everyone's an LLM expert. Uh,
um,
yeah.
I think since, I don't know, since the last few papers, you're almost fully transitioning to LLMs. Are you still doing
I guess
RL?
it's more RL related to LLMs, but then all LLMs are very funny objects, I would say.
Yeah.
So I guess I've started working a lot onto just LLMs too. But it's almost very, yeah, you'll see in today's talk, there's a lot of RL, but it doesn't look like that if you think in just LLM terms. Uh,
Yeah, let's hear about today's topic. I'm familiar with some of the works, but I would very much like to hear your takes. Okay, let's
yeah.
get started.
All right. Hopefully you guys see me and hear me and you see the slide change. So I will start right away. Yeah, hi everyone. My name is Rishabh, and I'm going to talk about some of our recent work. So the title of today's talk is Improving Large Language Models Using Self-Generated Data. Now, well, let's just start with what are large language models. So I guess these models basically you can think of as they take some text as input and they provide some text as output, and they're able to do many, many tasks. So here I'm showing like a bunch of tasks like translation, summarization, and I think some other tasks. I don't know what those are. But yeah, and we have a bunch of these things like GPT-4, Gemini, and whatnot. And how do we get these LLMs? So training these language models requires high quality data, and typically it's done in two stages, often called pre-training and I guess post-training or instruction tuning, which can include a lot of things. So pre-training is basically high quality data scraped from the web. That's the pre-training stage, which is the first thing you see on the top left. On the bottom, you see the post-training stage, where you basically have a lot of goal-oriented tasks. So you have a bunch of tasks, like as I was mentioning earlier, basically things like, well, why is the sky blue, or translation tasks, summarization tasks, and a lot of other things. But basically, this is the kind of data which is collected from humans rather than we are scraping this from web. But again, this is very high quality, often like very good kind of data examples that we have. Okay, and then I guess there is this question of, well, are we running out of high quality data? And I guess there is this research from I think this startup called Epoch AI, but basically they are showing that there is a possibility that we are basically running out of this sort of like high quality data at some point in time. And let's say if that happens, let's assume this is a scenario that we will run out of all the things we have on the internet, and maybe humans are going to be a bottleneck, and at some point we'll not have more data to train on. Let's assume if that is the scenario, then I guess a simple question you can ask is like, what if the models could generate their own training data? And I guess here I'm showing like an image of a robot writing something, which is going to be used to train that robot, just to bring that image to mind, that what is going on in this sort of a gene. Uh, so if let's say you're assuming that, then one thing is that if you naively do so, that can result in model collapse. And what could happen is something like, let's say the model makes some sort of mistakes. If you just try fitting the data model on its own data, those mistakes might be amplified, and then this can keep going on in a loop. And there's like a technical work which shows that. I guess an intuitive way to think about all this is, let's say you have a model which is 40% accurate, and now you just generate a lot of data on this task, and then you train the model again on all this data. You will find that because there was only 40% probability that a data point was good, you would basically be training the model on more wrong things than correct things, and that can further amplify as you keep training it more and more. So just naively doing the synthetic data training would not work. Hopefully, so far so good. Any questions? I'm guessing not, so I will continue. But yeah, for more details or technical details of like how other than the
Um,
example I gave you about like
I have a
this
question.
specific. Oh, we
So,
have a
so
question.
yeah, so this sounds right in theory, but has anyone proven that?
Yeah. So the paper I'm saying, the curse of recursion, they actually prove this, and they have a bunch of follow-ups.
I see.
That if you keep training the model on its own generated data, what happens is like the model. So the actual reason is, I think I've written this on the slide, which is the model is sampling something, and it's not sampling some other things. When you are training on its own data, it's just basically going to make the probability distribution even more peakier, in the sense that whatever it's sampling, it's going to say that this is even more likely. And basically that's going to shrink. And eventually what happens is the model just, at least on some of the image generation side of things, the model just generates noise. For text also, these folks have shown, some of these folks have shown that, oh, this can't doesn't collapse.
Yeah, it's like a human in an echo chamber, like reinforcing its own
Yeah,
bias.
yeah, you're just reinforcing your own. Yes, that's the sort of idea. So the reason is because there's no sort of like, yeah, we're just training on all of it. So I guess one pathway out of all this is like there are often a lot of problems where verification can be easier than generation. And what do I mean by that is, like, think about these two examples. So let's say you're trying to solve Sudoku puzzles. Uh, so solving a Sudoku puzzle is hard. Well, at least it's hard for me, and I'm guessing hard for a lot of people. But it's easy to actually check if someone gave you a solution to a Sudoku puzzle. You can just quickly verify because you know rules of the Sudoku puzzle and you know what are the constraints you need to like satisfy. So you can just easily solve it. Similarly, I guess if you think of like solving coding or doing programming, generating code can be hard depending on how difficult the problem is, but verifying that is easy if you're given access to test cases, because we can just like run the code on a bunch of different test cases and see whether we got them right or not, and that gives you some idea of how good or how correct the code was. So again, there are a lot of these problems where verification can be easier. So what we can do is we can generate data from the model, but then we can assume access to this sort of verification signal or assume access to some sort of feedback, which is whatever the data the model generates, we can evaluate how good that data was, at least for some of these tasks. And the hope is maybe we can expand these tasks as we get better and better models over time. But assume we are now focusing on tasks where this sort of verification is possible. Alrighty. So far so good, I'm guessing. Let me continue. So I guess one question is, how do we self-generate data for something like problem solving? So let's say I have this simple problem: a stock loses 10% its value on Monday, on Tuesday loses 20%, blah, blah, blah. And then you can ask the language model to generate responses. Basically, you can just sample from the language model at, let's say, a high temperature to get like these different kind of responses. And then you can verify which responses are correct or not based on whether it gets the right answer. Because let's say you're given access to the answer of this problem. And so basically, you, for each of the generated solution or responses, you check whether the response is correct or not based on the final answer correctness, and then you just fine tune the model on the data it generated, and you can repeat this process. So hopefully the people got this visualization, but this is the simple recipe for self-training. So I've covered the first part of the talk. So this is basically reinforced self-training. So what is the process? The process is you generate samples from the model and filter them using binary feedback. So if you go back to this image, you can see what I was doing. Basically, I generated a bunch of samples from the model. I had access to some sort of binary feedback here, whether the response or solution was correct or not. So this is the first step. And the second step is you just fine-tune the model on these samples, and you can repeat this process a bunch of times. And now for those of you who like math and understand math, basically the first step corresponds to E step, and the second one is M step. And well, remember, the only time you read E step and M step is in the context of expectation maximization. So you can actually prove that this process corresponds to expectation maximization based RL. I'm not going to go to the math, but if people are interested, you can check out the math. But the process is very simple. Hopefully everyone understood what the process is. That the first step is you generate samples and filter them, and the second step is you fine tune the model on these samples. And then this is done on the entire data set of problems or prompts or whatever you have, and then you can repeat this process again, which is you fine tune the model, and then you have a new model, so you can repeat the process again with that new model, and so on and so forth. Hopefully everyone got it, because I guess I'm going to be referencing this slide again and again. So this is probably, let's say, one of the key slides in this talk. If you didn't understand it, please just ask any question, because this is going to come back again like two,
Can
three
you
times.
explain in what sense it's a E step and an M step?
Can I say what is E step and M step?
No, could you explain in what sense? Like, what expectation are you looking at? And
Oh,
what
I
the
see. You're
maximization
asking.
sort of makes sense, I guess, because you're trying to fine tune on it. But the E step is not very clear to me.
Yeah, so E step is actually, there are two things happening in the E step at the same time, which is basically we are sampling from the model and we are also filtering. Filtering actually corresponds to sampling from an improved policy. So that's the E step. So that's the filtering part doing here. Like basically think of the policy. which is better than or think of the model which is better than my current model, and that is what we are taking the expectation with respect to. And that's why it's kind of hard to say without actually showing you the math. But think of the expectation is with respect to improved policy, because eventually we want to make the model better and better at, let's say, this problem solving task. And what we are doing is, first we are trying to find something which is better than my current model. That's the E step part. And the second step is just actually doing fine tuning to improve it.
Right. It makes sense now. Yeah. Okay. Thank you.
Yeah, and I guess maybe if you want more references, so this expectation maximization RL comes from a really old paper from Peter Dayan and Geoff Hinton from 1997. So it's actually very old. But anyways, let's continue.
So
Any other questions?
You mentioned that you would generate samples, you would go through the whole data set, but wouldn't it make sense to go through the samples that were wrong and by the current model?
What do you mean?
I would just like generate more samples from the problems that were not
that's true.
correct.
Yeah, so that does make sense. Although I guess for simplicity, generally what people do is they just treat each problem equally, and for each of them, let's say you generate 32 samples, and then you just pick the ones which were correct and discard others. But it does make sense that if, let's say, you probably want to get some samples for each problem. So the problems which you're not able to solve, you should spend more budget there. Although I don't know if people have tried this idea, but it does make a lot of sense if you want to use your sampling budget more efficiently. That for some problems are really easy, you just get the answers right away, even if you sample 8 times. But other problems, you might need to sample, let's say, more than 64 times to get something reasonable. So
yeah, and I can guess this it would improve problems where the correct answer is in the samples. But what if the LM is so bad that however many times you sample for some questions just cannot get it right?
So you're already pointing out like some of the problems with this approach, but let's just do this is the simplest version. And yeah, assume that the model is good at some problems and not good at others, and then you can improve iteratively because you are improving the model over time. Someone did ask a very interesting question, or there's a bunch of things I see in chat. I guess I am going to go over some of these. Well, I guess, let's see, this sounds more like policy filtration. This seems to me rejection sampling, then doing amortized inference. Well, they're both related. So EM framework is more general, but here it's like that. This seems to should be using model done and thoughts. Yeah, so I guess I'm going to cover a bunch of these questions as we go along the talk. But yeah, they're all good questions and maybe opportunities for follow-ups. Anyways, okay. So people,
also, I had another question. So it's not very clear to me, and I don't know if it's intended to be clear at this point in the presentation either. But the problem that you set out describing, on when you try to train on synthetic data, you're sort of amplifying the modes and then losing the long tails, right? How does this solve that? Is that like?
Oh no. So I guess the problem there was no sort of filtering going on. So think of tasks where we do have some sort of verification signal. There we can use model generated data. So I guess I'm focusing on, let's say earlier we couldn't really use synthetic data in the sense that there is always this risk of collapse. But here I'm saying, what if you have access to some sort of evaluation signal? So that's the extra thing I assumed, which I motivated by saying that there are a lot of problems where verification or this evaluation signal is easier to obtain than actually generation. And things like math problems or coding problems, that's the examples I'm giving. But then I guess ideally, where do this evaluation signal comes from is another problem. And can we actually apply this on broadly?
Not just that, I think there's also this question of, I think even the probing questions that you're asking in the first place, they're supposed to somehow probe into those long tails. Unless you do that, it would be somewhat better than just vanilla training, iterating of the synthetic data, but then it won't be foolproof because you're not necessarily probing the long tails, right?
Yeah. So, also, I guess again another thing is it's not fully synthetic in the sense that the problems are human written at the end of the day. So again, this is like think of this as the baby step 0 of the full synthetic data process, and I'm just describing that one, I guess.
Makes sense. Okay.
Cool. Any other questions, comments? If not, I'll move on. Okay, I guess anything else. So what kind of tasks I'm going to be talking about right after this? So I guess we looked at these 2 tasks in this work, which was Hendrik's math, and I'm just giving you a problem and corresponding solution to just give you a feel of what these tasks look like. These are not trivial, or at least require some reasonable amount of knowledge. and also a little reasoning skills. And similarly, these coding tasks are from introductory programming competitions. So again, you can look at these problems just to get a feel of what kind of problems are we talking about, am I talking about, when I'm going to look at the efficacy of these methods. All right. So hopefully this quick look was enough. But yeah, people got a feel of like, okay, these are like somewhat non-trivial problems. Um, okay, so the first interesting result we got was that actually fine-tuning on model-generated data filtered using this reward signal of whether we got the answer right or not actually outperforms fine-tuning on human-written solutions, because these data sets are problem-solution pairs where both problems and solutions came from humans. And we found that we can fine tune the model on those solutions. But if you just generate the data from the model itself and then just fine tune on those filtered solution, which is this approach called ResTM I just described, that actually does much better than finding on human written solutions. And the other thing I'm showing is I'm actually showing results across multiple iterations for two different model sizes. These are PALM2S and PALM2L. These are like large language models from a couple of years ago. And you can see as we increase the number of iterations, performance improves, but it does seem to have diminishing returns as we go from iteration 1 to 2 to 3. And the other thing I'm showing is we also reported performance, or basically transfer to a data set which was we didn't train on. We're just evaluating performance on this data. So this is like think of this as a held out data set altogether, which is not like, so in Hendrix math, we have a training data set and test data set. So this is something like in distribution performance or generalization. You can think of GSM-8K as somewhat outer distribution generalization. These are like a simpler set of problems than this Hendrix math, but here we're just evaluating transfer performance. And you can see also another interesting thing, more iterations help on this math data set on which we were training and evaluating. But on GSM-8K, more iterations start to hurt. So this kind of indicates there is a little bit of task-specific overfitting going on, that the model becomes really good at solving math problems in distribution, but outer distribution, it degrades a little bit. Hopefully this is good. But yeah, the main result, I guess, just to keep in mind, is the fine-tuning on expert solution or expert demonstrations or human written solutions here was not as good compared to, let's say, fine-tuning on these model generated solutions, which we filtered. All right. And
sorry, I missed where do you get the binary feedback from for the model generated
so for
solutions?
math, I guess we have access to the final answers. So again, similar to these, if we go back to the slide, we can check whether the answer matches, the answer of the LLM generated solution matches the final answer. So it's not the perfect binary feedback, but it is basically telling you whether you got the right answer or not. That's the feedback.
And that could be a non-trivial test, check, right? Because there's different ways of phrasing the answer. So you need some way of comparing the answer to the
yes,
whatever.
you need to extract the answer. So basically, the LLM response, you need to somehow be able to extract some answer, but assuming it's a math problem. So we have like, if you look at how these things are done, there are complicated regexes, or people use another model to extract the answer from the response.
So in some sense, for math, this may be fairly straightforward because you have maybe values, numerical values and such. But if it involved some abstract concept, then it's a much harder problem to actually
then I
determine
think
the
what
correct.
people are so for those harder problems, what people have resorted to doing is using another language model to evaluate.
Sure. Then,
but it is, again, it's actually an open research problem. Like, how do you actually even do the simple sort of extraction? So this was for math. Any other questions? All right. So we actually saw similar results for coding too. So here I'm showing results on the coding benchmark, although here you see overfitting much more prominently. So here we actually start seeing overfitting, and because I think we only had the reason I think here was that we didn't have that many test cases. So there was a bigger risk of false positives, that whatever program the language model write, it only had to pass like a couple of test cases, and it's possible to pass the test cases but not actually writing the correct thing. So that could become like false positive could have been a big issue on this data set again. But the same sort of finding holds, that fine tuning on human written expert solutions was actually worse than fine-tuning on model-generated solutions. And I'm showing results again for two different sizes of models. This is like the PALM2L and PALM2S star, I guess here. Forget about the star. Just think of it as like a small, capable model. And we also evaluate transfer performance on this thing called human eval, which is the de facto standard for how people evaluate coding performance in language models. And we show a huge transfer performance. So basically, just training on this apps data set, we were able to improve human eval performance by 10%, which is actually pretty significant. All right.
Question, is there a disparity in the data size between like the human expert data and the, because like here,
yeah, that's actually a very good question. I will, so there, because you can generate a lot more solutions from the model, definitely here we're using a lot more of those, but I will come to this apple to apple comparison. But that's a very good point. So what I guess the person asked was, we only have one solution for each problem or each in the human data set, but if you're generating solutions from the model, you can generate like a lot of different kind of solutions. So there is a lot more data when we are using. And are the gains coming from just more data, or is it actually better data? I will come to this question, but that's a good, yeah, that's a great question. Anything else? Okay, I guess I'm not asking anything else. So, and I guess maybe one thing I would want to show is overfitting is actually an issue. So what I'm showing here is like the performance on the training problems versus performance on the test. And you can see that, so that is shown in blue. The training performance is blue across iterations, while the test performance is orange. And you can see the training performance goes up quite quickly, while the test performance actually starts saturating pretty, or at least does not grow as fast and also starts saturating, while in the case of apps, it actually starts going down. So you can see that there was like, at least the models are overfitting even as we do more and more iterations. And I think the reason could be they're really getting good at solving the current training problems, because we only have, for math, we only have around, I think, 5K problems that we are training on. On apps, it's even smaller. It's 3K. And that's why maybe on apps, the issue seems more prominent, because it's even a smaller data set. And also false positives are another issue, which might be happening. All right. And I guess maybe just one quick plot, pass it K performance, which is, let's say if you give the model K attempts to get an answer, that is also improving after this fine tuning. So that's good, which is the model is not losing diversity too much. That if you just give the model K attempts to solve a problem, one of those attempts is often correct. And you can see that the orange line is obviously higher than the blue one, which means that the model is improving in that sort of ability too. So it's not just the biggest gains are coming at pass it one, which is if I just give the model one attempt to solve the problem, but the gains stay, or at least there are still some gains if you do multiple attempts. Okay. And then I think just someone just now asked this question. Well, I told you that fine tuning on model generated data was doing much better than fine tuning on human written solutions. Now, where are the gains coming from? So this is that experiment. So we have actually a total of 7K problems in the training set, and we have human written solutions for all of those. So that's SFT 7K. We actually only managed to solve or 5K problems in the training set with model generation itself. So for 2K problems, we didn't get any solution at all. For the remaining 5K problems, we did get at least one or more solutions. So I'm putting this SFT 5K as a reference there. Then rest EM 5K is basically for each problem, we have multiple solutions. So the red bar basically shows here that we were just fine tuning on all of these. And the rest star 5K, the green bar, is the one where we just use one solution for each of these 5K problems. And this kind of shows that if you were to do apple to apple comparison, the data quality is also better, or at least the model prefers learning from its own data rather than using the human written examples or solutions.
Have you looked at why those 2K fail, and could you like use those as test cases after you've done the rest star or the rest EM, whatever? Because
I guess those were like the.
He's a little, I don't want to say suspect, but it's a little off that.
So the thing is, this data set has like 5 different difficulty levels.
I see.
So basically, it's like easy to really hard, and I think we
But
basically managed to solve.
wouldn't the test set sort of also be stratified with those levels?
So test set also has the case. So that's why like this is evaluating performance on test set, but the 2K problems were in the really, really hard category, mostly, and then hard category. Like it's the hardest categories which we couldn't solve.
So those are also failing on the tests then? Is that true?
Yeah, it's also failing on it. That's why you see performance is only 40%, right? It's not like the test. It is also failing quite a lot on the test problems.
Got it. Okay, so then, yeah, definitely it seems like the data quality is just better, right? That's clear.
Well, there's a bunch of hypotheses. So one could be that the model just likes on policy distribution. I can actually give you a very good hand wavy argument. So I guess maybe this is my intuition. So let's say there is some problem which requires knowledge of integrals to solve it. If the model doesn't know how to solve integrals or just doesn't know the fact about integrals, you can put that in the human written solution, but the model wouldn't really learn anything from it. While when you're generating solutions from the model itself, it's only using the capabilities it has or whatever skills or knowledge it knows to generate the solution and the answer. So basically, you're not using things which the model doesn't know. And I think this is one of the hypotheses of or the underlying reason why model generated solutions could be better. The other is the formatting and all those other things like model. When you're generating solutions from the model, this is the distribution which model generates. It's possible the distribution of human written solutions is very, very different or far away. Even though the models have been pre-trained on all of internet, it's still very possible that there is a distribution mismatch, and that might be another factor. So there's a bunch of these competing hypotheses going on, but this has been confirmed in other works too, that models like their own generated data, or LLMs like data from other LLMs more than humans if they are filtered for quality.
So how does that last bit about the distribution mismatch, how is that? I guess it does solve that. Yeah, I was trying to understand how that's solved when you do model generated, but I suppose that would, because you're sort of now sampling from the model that the data, sorry, the data that the model understands. So yeah, okay.
Cool. Do I have other? Yeah, and I guess maybe one quick result I want to show is we did eval on. It's like funny, we did this eval. So this is like an eval where you have to hand grade the solutions generated by the model because there's no easy way to do this automatic verification because there's a rubric. This is like an exam, a high school exam in Hungary. I think one of the LLM providers, like I think Grok, did this eval. So we thought, okay, we'll do this too. And this is held out in the sense that this came after we did the fine tuning and the pre-training. So basically, there's no way that this kind of data was contaminated in some sense because the exam was written much later, and we found that the checkpoint we fine-tuned actually transfers very well. So this PALM2L REST EM, you see that it's doing very well both on this GSM 8K, which is an existing benchmark for high school math evaluation, and this Hungarian high school final results is also doing pretty well. So this is a good sign saying, okay, we actually improved some of the simple math problem solving capabilities of the model. All right, I think this was the last slide of this. For more details, look at this paper, Beyond Human Data. So I guess what are the things we learned so far? So first thing was self-generated data can improve performance given a reliable reward. And I guess so the second thing is it can even outperform human data. And I guess I just wrote one reason here, but there might be other reasons also possible. So far, so good. I think we're going decent on time. Any questions for the first half?
I guess you can make human data in distribution or sort of by asking model to rewrite it.
Yes. I think people did that, and that actually does help a lot more. So the in-distribution hypothesis has some weight because, yeah, you can basically take the human solution and ask the model to rewrite it, and that might actually help more in some sense. I think it was still worse than model generated because, again, the kind of skill issue might come up. Like, let's say the model doesn't know what to do with an integral, human solution uses it, then you're basically teaching the model to blindly copy that thing without even understanding what does it mean to do an integral. So that might be a bigger issue which we can't tackle. Okay, so let's revisit this. And as I said, actually, we'll be bringing this slide again and again. So here is it, the second time. So what was the process? The process was generate samples from the model and filter them using binary feedback and fine-tune the model on these samples. I've highlighted this filter them using binary feedback. And there's a bunch of problems in this, but I'm going to talk about one of them. What do you think I'm going to talk about? It's very simple. I'll maybe ask like people here. Yeah, and I think some people mentioned in chat also, but there are a bunch of issues. What could be one of the issues with this binary feedback filtering?
So binary signal is not fine-grained enough. Some probably it's wrong, but like it's very close to the correct answer. You want to give it some weight.
Yeah, that's fair. But assume I only have binary feedback. Assume I don't have anything more than that because it's very hard to get this sort of thing. Assume I can only check whether you get the right answer or not. So let's say we stick to binary feedback. Any other sort of thing? what is, yeah, and think about it, there are only two steps. So what could be going wrong? And I guess the hint is someone in chat already mentioned something around this, but yeah, I don't want people to just go through chat now.
Yeah, people are saying that doesn't use the wrong examples. And
Yeah,
what
that is actually it. So this is like basically we discard like a large number of incorrect solutions, especially let's say the problems for which we have only, let's say, one correct solution and everything else is incorrect. But there is something to be learned from incorrect solutions too, right? Like let's say if you are solving these problems, you get something wrong, you actually figure out, okay, what happened here, or sort of stuff like that. But here we are discarding all these incorrect solutions, and maybe potentially there is a lot of valuable information in this. So this is like the kind of second problem I'm going to focus on. So what are we going to use these incorrect solutions for? Well, the simplest thing, or one of the simple things you can do, is you can train these things called verifiers. And now what is a verifier? So again, let's come back to this slide I showed you earlier. So we have this problem of stock loses whatever value, and here's what this is. The language model generates responses, and we still have our final answer correctness response, right? Now what we can do is we can train a verifier, which is basically a classifier or reward model of some sort, which is telling me whether a generated solution given a problem is correct or not. Now, why the hell do you want to do that? Can anyone say here? Like, what's the point of doing this, training this verifier? No one?
Couldn't you just look at more fine-grained information from that rather than asking it to? I mean, I'm pretty sure that's not what you're doing, but all that comes to
No,
my
but
head.
like think about, I don't have fine-grained information because where do I get it from? But I do have these correctness. I do have this binary feedback, and I can train this verifier. I'm asking, why do you want to even do that? This is actually a very common thing to do for these reasoning style problems, that we have this learned verifier. Like, what do I? Let's say if I have this learned verifier, what do I use it for?
So once you have something like that, I think it's kind of like a little bit like knowledge distillation, where you could sort of, so if you learn something like that, it could sort of be slightly wrong, but in a reasonable way on the filtering, right? Where you could have responses that are somewhat similar to the correct responses still being labeled, have a high probability of correctness, right? And you could threshold on that, I suppose, right? Rather than just doing
That's a good thing. So yeah, so there's a bunch of good answers, and I guess the last two ones I like in the chat, and these are already like sort of follow-ups. Like there are different papers for each of these two things. But like simplest thing you can think of is at test time, you can use this verifier because you don't have access to the final answer at test time because you want to solve these problems. So you can't assume that you know the answer already. Otherwise, what's the point? What you can do is you can use this verifier to select which one is the most likely to be correct. And that is a very simple case. And I think the other folks in the chat mentioned two different things. You can use the confidence predictions of the verifier, maybe even during training. But like the simple thing is to use that at test time. And the other thing is you can also train on problems on which we don't have the answers, right? For some training problems, we don't have the ground truth answers. We just have the problem. Maybe you can hope the verifier generalizes and use that. So those are like pretty good follow-ups. But here, I guess the very simple thing is this. So how do we use a verifier? We basically give it the problem. Let's say at test time, the language model generates some solutions. We pass it through the verifier, and the verifier gives me a probability or some sort of score, even if it's not giving me a probability of how likely the solution is correct. And we can just use the score for ranking these solutions and pick the best one. That's like the easiest way to use a verifier. And assume if your verifier is actually it's a good verifier. Let's say it can actually figure out incorrect from correct, because that's what you trained the verifier to do in this process. Then hopefully there is some benefit of the selection. Does this sound good? I guess hopefully people understood. So let me show what we did. So I guess the simple idea is this. Again, come back to the slide. We said we are discarding a lot of these incorrect solutions. The verifier is a classifier. It needs to use both correct and incorrect solutions. So what we are doing is basically we're augmenting this REST-TM thing with the verifier, which is rather than discarding the incorrect solutions, we are using these to train this verifier. And then we can repeat this in the iterative process. And there are some details I'm not going to go into, but basically the high-level idea looks like you generate solutions for each of the problem. Then for correct solutions, you fine-tune your generator or the model you want to solve the problem with. while you train your verifier on the side using both the incorrect and correct solutions, and you can repeat this process at each iteration. At test time, you generate multiple solutions using your generator, and then you verify using your verifier and pick the best one. That's like one of the simple ways how people use verifier. And then there's a lot more things we can do with verifier, improve training, and maybe more fancier ways of using it at test time. So far, so good. Hopefully people understood. Any questions?
Quick question. During the test time, how many potential solutions do you generate, like in the order of magnitude? 10?
We can do, so typically, well, depends on the paper. People have gone up to like 1,000 solutions. In this work, I think we generate up to 256 solution per problem. And I guess I'll also compare to some baselines or other ways of using so many solutions, because you are using a lot more compute at inference time.
And those are mainly from different kind of sampling technique?
No, it's just it's just high temperature sampling typically. We don't even change the sampling technique. It's just temperature sample. We just sample from the model at temperature 1 multiple times, and that gives you some diversity of solutions.
Got it.
And I think maybe just to go back to like why this makes sense, let me quickly go back some slides. So this thing I mentioned, positive k, which is if I were to give the model k attempts of solving a problem, you can see performance goes up quite quickly. And here I have, let's say, the best possible verifier, which is if any of the k solutions is correct, I just pick that. So here the verifier is actually the Oracle verifier, which is I know exactly which solution is correct or not. We are just substituting that to the learned verifier. And that's why this idea works really well. Or the idea of using a verifier is very common in these reasoning style problems. All right, let me move forward. So how does results look like? So here again, I'm comparing like, I guess here we change the task a little bit because these are different models. So these is Llama 2, 7B, 13B models, and we're evaluating on GSM 8K and MVP, or we trained on GSM 8K and MBPP, and then transferred on the test set of these problems as well as new data sets. So you can see SFT is the blue bar. If you just do ResTM, which is just the thing I described before, that gets you like a pretty nice improvement. If you do verification on top of the SFT policy, that actually gives you an even bigger improvement because now you're using a lot more compute at inference time. And then the red bar is the V star is the other thing, which is combining verification with ResTM. So you can see that across the board, this thing is working really well. Okay. So I guess one thing we also saw was like, I guess here I'm comparing performances across iterations. As I said, we are running 3 iterations of ResTM earlier. Here we are doing 3 iterations of the generator and 3 iterations for the verifier, which is like in each iteration we generate some data. We fine tune the generator only on the correct solutions, while for verifier we use both the incorrect and correct solutions. And you can see both of them matter. You get slightly more gains from actually the verifier than the generator. But you can see as you go across any of the verified iterations, performance improves. And also as you go across, as you improve the generators, performance improves too. All right. And I guess one baseline, which I mentioned, this is not applicable to coding problems, but anywhere when we can extract a final answer, because for coding, we are generating code. But for math problems, we can extract a final answer often. What you can do, and this is like a simpler approach, is you generate multiple solutions, you extract the answers, and then you just pick the majority voted answer. So here you are basically comparing with a fair amount of inference or equal amount of inference compute, which is the LLM is generating a lot of solutions. One way is to run them through a verifier and pick the best one. The other is just extract the answer for each of the solutions and pick the one based on majority voting, like the answer which was generated the most among these solutions. And that's like a non-trivial baseline. But so hopefully people understood what this baseline is. And this V-star thingy also outperforms that baseline. So here majority voting is blue, and you can see that we are going up to 128 solutions or completions per problem. And then the green line is the third iteration of the V-star thingy where we have the same generator in all these plots, which is the final ResTM LLM we have. But we are changing whether we are using a verifier or we are using this majority voting approach. Hopefully this makes sense. Okay, so I guess this was the last slide of this part of the talk. I guess, and maybe I'll ask for questions here. So what are the things we learned so far? And I guess this is the thing we just learned. We can train a verifier using both correct and incorrect solutions. Maybe any questions at this point?
There's a question in the chat about why we need a DPO.
Yeah, that's actually a good question. So I think there's a bunch of reasons I can give you, somewhat hand wavy, but we were using LoRa, And typically we just train a classifier within language modeling loss. So we have a classification objective for incorrect, correct, plus a language modeling objective to regularize the model a little bit. DPO actually combines these two. So DPO is just like another way, because you can think of a verifier as a reward model, and we just made the connection and said, well, why not try DPO? Now, we were using LoRa adapters, and we found that with LoRa, we could not train the verifiers in this classification plus language modeling objective that well, while DPO worked much better for us for training the verifier. But these are like trying to do the same thing. The other thing is, I guess maybe the hand wave reason why I can say why DPO worked better for us than this thing was that if you think of false positives, like solutions which get the right answer for the wrong reason, DPO only says, DPO is a contrastive objective, so it's only comparing two things at a time. So it's saying, oh, this thing is better than this other thing. While if you're training a classification objective, you say, oh, this false positive is actually good. So you're absolutely saying something is good, while DPO is saying, oh, this is better than negative. So there's that too. But it's an empirical thing. We did compare to standard verifiers, which are just classifiers, and that did not work as well for us with LoRa adapters. But generally, people do just classifier plus language modeling objective train these. That said, I guess I would say people have done this without DPO, and this works also. Like you can use your favorite method for training your verifier. Okay. I guess I don't see any other things. Okay. So I guess we are at the last part of the talk. So let me revisit this again. So I told you about this process, which is we are generating samples from the model and filtering them using binary feedback. And then we are fine-tuning the model on these samples, right? And now I've highlighted fine-tuning part. What could be well, there's nothing problematic with it, but what could be like something I'm saying here? Why have I highlighted fine-tuning here? Like any guesses, people who work with language models? I'm saying, and now I'm going after this fine-tuning part. Like I'm saying, no, I don't like this. What are we going to do with it? Like
maybe
anything you can think
something
of?
got forgotten during the fine tuning.
Yeah, so I'm not saying there's any problem with it. Well, I guess there is one thing with it. It requires a lot of compute. And let's say most people can't even run fine tuning. Let's say you are in academia or you don't have access to these, you only have access to these APIs of these models. You can't run fine tuning. Like only I have access to model checkpoints and I can run it. And even if I have access to the checkpoint, I need a lot of computing resources to do this fine tuning. So there's a bunch of issues, but there's nothing fundamentally wrong with it. But yeah, that is true. Fine tuning can, what you said was also true, which is fine tuning can result in overfitting to a specific task. Because the language model is a general model, it can solve a lot of different tasks, but now you're fine tuning on some specialized tasks that can lose knowledge in other tasks. There is that sort of possible issues which can happen. Yeah, Roseanne said prompting is all you need. Yeah, so I think someone told me a very similar thing. They're like, oh, this fine tuning, like, is fine tuning really needed? And I was like, what? Really? Is that the case? So I thought, okay, I'll just verify it myself, because people told me that, yeah, fine tuning is not needed these days. Prompting is the future. So I thought, okay, let me see how good the future looks like. So I went to see, okay, let's just evaluate. So let me just give you a background. So what I'm going to do, we are going to actually try in context learning or prompting. So here, basically, I'm talking about few-shot prompting here, where let's say you want to solve some task like translate English to French. So what people have shown, so this was shown in the GPT-3 paper, that you just give me some examples. So here I'm showing you a bunch of examples, and then ask the task you want to do in the prompt. So here I want to translate cheese, and the model can just do it. So there's no gradient updates are performed. We are just showing the model the task definition and then a bunch of examples for this task, right? So, and this has been shown to work really well with GPT-3 and other language models. And well, this is much easier to do than fine-tuning. It's unclear how well this performs. Now, recently what change happened was that the context window of these models expanded. So GPT-3 had a context window of 2000 tokens, which means you can put like a few sentences or only a few examples. But now we have a context window of 1,000,000 tokens with some of the models like Gemini. So that is around, I don't know, we can compare 2000. This is like 100x. So two order of magnitudes bigger. So we recently had this work where we said, well, what if we just send the model hundreds or even thousands of shots, or sometimes 8,000 if you look at the sequential parity task. And well, it worked. The model actually can learn about the task if you just send it a lot of examples. So this was a bit surprising, but basically the model can learn from a lot of examples. So we thought, okay, now if we have the ability to put like thousands of examples. What if we just, rather than doing fine tuning, we just put these examples on the prompt? And so basically, we get this thing called in-context ResTM, which we call reinforced ICL, because ResTM corresponds for reinforced self-training. Now it's reinforced in-context learning. So what are the steps? The steps are, again, very similar. Each step remains the same, or the first step is to generate samples from the model and filter them using binary feedback. The second step changes. Now, rather than fine-tuning, we just put these problem solution pairs in context for the model. Any questions so far?
Any specific order or just random?
Just random order. I guess I'm not good at prompting, so. And also now you're putting thousands of examples, so I guess it's unclear how much ordering would still matter, but maybe it matters less so because there's not like few examples. Okay. The other thing is this model is actually, sorry, yeah.
Do you still even need to train the verifier, or can that also just be in contextified, no LoRa needed?
Yeah. Well, if in-context learning is the future, well, we don't know what the future looks like, but yeah, it can be, I guess. So we do actually have it's funny you asked this question. So let me go to this. There is a code verifier task here, if you look at that. And basically, we did manage to actually learn a verifier in context also. And the verifier was basically just checking for correctness. So if you look at this code verifier bar, I think it's, it's before big bench and after classification. I don't know if you see my pointer, but we actually managed to see that, a 128 shot prompt is able to do much better and is learning a reasonable verifier that we do get like a 5% improvement in performance with the generative. Anyways, we can do it. I guess that's a short answer if you wanted to. Okay, so so this is the simple extension. And I guess one baseline, which is like the funny baseline I should describe, we tried was like, rather than sending problem solutions, what if we just send problems? Because one hypothesis is that the models are just mostly doing some sort of retrieval. They already have all the knowledge they needed to solve these tasks, especially the tasks which are very popular for benchmarking. So we also tried something else. I'll cover that too. But that is like, think of that as a baseline, which is rather than sending problem solutions, what we just send problem, and then give some formatting instruction to the model. So that is very like, that we call it unsupervised ICL. Here is what the results look like. And maybe I'll take like a couple minutes to describe what the results are. So I'm showing like the standard 4-shot prompt that we use on this benchmark. That's shown as the horizontal line. Then I'm showing you a number of shots on the x-axis. So we tried up to 500 shots. This is actually a lot of tokens. I think it's around 200K tokens. More shots seem to be like similar. Yeah, it's saturated, I think, or something like that. That's why we don't show it here. Now, there are 3 kinds of data sets here. The ICL ground truth correspond to using ground truth solutions. Reinforced ICL is the approach I just mentioned, which is we use model-generated solutions. And you can see that the blue bars are generally higher or better than the green bars. First of all, one general trend you see is as you put more shots, generally it helps. After a point, it starts to saturate or degrade. And blue bars are generally higher than the green bars. That's one. The other is the unsupervised ICL thing actually can even work better than both these reinforced and ICL on the original task we were collecting data on, which is this Math 500 data test set. While on the transfer task, I guess there was still some value to this reinforced ICL thing, that the blue bars are generally slightly better than the green, the 2 colors of green. Yeah, I don't know. Basically, here it does seem like putting a lot of shots does help, but putting just the problems can also help quite well. But if you're looking at an unseen task, then the solutions did help a little bit more. So this is one, and maybe I'll present another where actually the unsupervised ICL thing did not work as well. So here, this is big bench hard. This is a bunch of these simple algorithmic and symbolic reasoning tasks. And here we went from 3 shots to 100 shots because we only had 100 shots. And you can see, again, the reinforced ICL thing improves in performance as we increase the number of shots. And it does better overall than both the human return 3-shot prompt and unsupervised ICL. So here, actually, we didn't have chain of thoughts. We only had, again, similar to like the setup, we didn't even have human written solutions. We only had 3 of these. So we only have final answer. So we had to generate the chain of thoughts from the model itself. And unsupervised ICL is, okay, don't worry about these solutions. Just send the problems and some formatting instruction. And that's it. Yeah.
Sorry, I missed something. So unsupervised ICL means you're just giving the problem statement, not the answers, correct?
Yes, problem, and then you're giving some formatting instruction with a few short prompt or some zero shot instruction. So because you need to actually generate the solution, so you need to tell the model that you want this out of it.
Okay, and reinforced means you're using the verifier to generate.
Oh no, reinforced mean you're just using the model to generate the solutions and filtering it with the binary feedback we have access to. So you're just using model generated solutions rather than the
yeah, that's what okay, no, that's what I meant. Okay, yeah, as opposed to human generated.
Yeah, human generated. That is, I think, the. So let me go back to the slides. I guess this is the plot I showed where the light green is the human generated or ground truth solutions. So basically, a similar thing holds as we saw for fine tuning, that in context learning with model generated solutions is better than in context learning with, I guess, human written solutions. But then unsupervised ICL is a strong baseline for these popular benchmarks. But then for other tasks, reinforced ICL is generally better because I guess.
And do you have some examples where the number of human generated solutions is just very limited, but with your method you could generate like orders of magnitude more training samples?
I guess this was, well, we don't have order of well, this is, I guess, that example, one example where we actually did not have any human written solutions. We only had the answers. But we could generate up to 100 solutions. And if we had more problems, because here I think we're limited by the size of the training set. We only had 100 problems. But if we had more, we could have just generated solutions for all of these. All right, and I guess maybe this is like a different talk. Which I'll not go to that slide.
From which paper is this benchmark?
The Big Bench Hard?
Yeah.
You just search Big Bench Hard. That's the paper title.
Okay, thanks.
It's I think a small subset of 23 tasks which are hard from Big Bench, which is a very popular, or used to be a very popular benchmark. Okay, so things I think we learned from this part of the talk was that we can possibly substitute fine-tuning with ICL, but it's to be seen how well in-context learning works, and maybe future models would have even better in-context learning abilities. So more and more of, let's say, things can be put in context instead of using fine-tuning. And I guess that provides you really a lot of flexibility of doing a lot of things.
Can I ask a question?
Yeah.
So when you do the ICL, you could also use a verifier with many different contexts, right?
Yes, you can do that totally. I guess these are all very interesting follow-ups. We haven't done any of that. But yeah, you can indeed substitute the generator with this ICL or many shot prompted model, and then this will generate different solutions, and then you can use the verifier on that. And the verifier itself, as someone mentioned, could be a few shot or many shot prompted model, basically, rather than training it especially.
Okay, got it.
Has anybody figured out how to improve ICL with negative examples?
There are papers, but I guess there you have to basically highlight things like what are the mistakes. There is one or two papers which can show that we can use how to use negative examples in context for improving generation performance. But I guess a more typical use case would be to learn a verifier. That will be more straightforward, that you show both positive and negative, and then there you have a verifier. But you can use it to improve generator. That's
well, I mean, based on what you talked about earlier, I mean, the next logical step would be to do ICL, but generate both positive and negative examples and use them somehow to improve the.
Yeah, I guess so. The straightforward extension would be to just have an ICL verifier and an ICL generator. But I guess there might be more interesting.
Well, the verifier could be any kind, right? It doesn't have to be ICL.
Yeah. I'm just saying that will be the easier version in the sense that we have to fine-tune a verifier. What if we can also just do in-context learning for that? And now that gives you even more flexibility because there's no training involved anywhere. It's just data generation and ICL. And then maybe you can iteratively do things, I think.
Yeah. Someone had a very important question in the chat earlier. Is the ICL with this many shots really, usable in practice?
Yeah, so I think we have things like basically KV caching, which can amortize the cost quite a bit. And Google, for example, at least for its model, serves that, which is if it's a fixed prompt, which is, let's say you have this 1,000-shot prompt.
Sure.
You basically know always that this is the prompt, so you can do a lot of optimizations. So it is usable, but there is a bunch of optimizations you can do. I think what ICL provides is the flexibility, and you can think of it as basically maybe a lower bound for fine tuning, or at least this is how I think of in context learning often, that this gives me much more flexibility to try out things quickly, and then eventually maybe I will go to fine tuning or maybe not, depending on how well ICL worked. Okay, I think we are very close to time, so maybe I can stop here. I don't know if anyone has last questions, but yeah, I will make the slides public, and hopefully you guys enjoyed the talk. Okay, I think I'll say bye.
Any other questions? Maybe one final one.
I do want to ask a fun question, right?
Yeah.
You can use verifier on the verifier too, right? You know,
You can, yes.
Oh, it's
And
meta.
version can you do?
I think the first version would help. The second one probably would, like, yeah, you can do one more, but well, you can always go deeper. I've seen the meme, so I feel like unless someone tries it, I wouldn't know. But I think you can verify the verifier. That does seem like a reasonable thing to do.
So on a more serious note, right? You know, how about human in the loop? When the verifier is not sure, you can involve human and then maybe vastly improve.
Yeah, so I think, yeah, you can think of verifiers as models, and maybe one question is these models are making mistakes, and right now we should be able to fixing those. That was the iterative process, that whatever the verifier was making mistake, we train on those things so that to get a better verifier over time. But maybe the feedback was very limited in the sense that we can still have false positives. So the verifier's reasoning was wrong, but it still verified and said, oh, you got the right answer. So the verifier's answer was correct, but reasoning wrong. And those are the kind of things we can fix if we had human in the loop. But then putting human in the loop makes everything very expensive. And I guess it doesn't scale that easily. So there's that question as usual.
Great, thanks.
All right, cool. Bye, guys.
Thank you. Bye.
Thanks, guys. Take care.